Okay, hello, welcome back. This is going to be chapter 14, a continuation of um, the last lecture and video that I posted. Not really a lecture, but a video. But this one's going to mainly focus on reactions with our favorite compound here, which is benzene. And this is going to deal with aromaticity as well. So just a quick recap. In the last video, we talked about how molecules, especially aromatic ones, they want to be aromatic because aromatic molecules are very stable, right? And we mean very stable because they have these delocalized pi electrons here, right? So because of these delocalized pi electrons, their charge is evenly distributed, and that makes it very stable. And remember our rules for aromaticity, we have one where it's the pi electrons have to satisfy 4n plus 2, where n is any integer. We have the fact that they have to be planar in the same plane, right, sp2 hybridized. And we also have the fact that um, each pi bond has to be conjugated from one another, right? And that is how you can tell if something is aromatic. And again, it's stable because we have this equal sharing of electrons, and that makes the charge evenly distributed, right? So we're going to be dealing with benzenes today, and we're going to be dealing with how they react. So we're going to be seeing a lot of these hexagons with these double bonds, and these double bonds are in fact, they are similar to alkenes, and we've seen alkenes before, right? In this reaction, we can react this alkene with this hydrogen and that bromine, where hydrogen is our electrophile, and then bromine is, after it leaves, it's going to become our nucleophile, right? So we can react it like that. And then the positive charge can either go on carbon number 2 or carbon number 3. But it doesn't matter because this molecule is planar. So we're just going to put it on carbon number 2, right? And then we just have that bromine that left, which now has a negative charge. And then we can just attack it right there. We don't have to worry about stereocenters because it's not chiral. And then we have ourselves a nice compound here, right? Pretty simple. We've seen this before with alkenes and alkynes. So let's look at the general reaction. I said that I said that hydrogen is gonna act as our electrophile, right? And we have here E as an electrophile, and then the leaving group, which was bromine, is going to react as our nucleophile. And again, the general reaction is it attacks an electrophile because it has a delta positive, and then this nucleophile has a delta negative, and then it gains that electrophile on either carbon number 2 or carbon number 3. It doesn't matter in this case. We can have that positive there, and we have that nucleophile that just left, which is now a negative charge. It can attack, and then we get this compound, right? Everyone's happy. It looks good. Nothing to complain. Okay. So let's apply this in a benzene. Okay. So this is a benzene, right? So we have any of these double bonds that you want to take. I'll take this one. So we're going to react it. It takes the electrophile, and then the nucleophile leaves, right? And then we get this intermediate where the electrophile can either go on this carbon or this carbon. I put it on this carbon, again, it doesn't matter. But then we also have this positive charge right here. And remember that there is resonance here. You can form resonance structures here, but I'm not going to do that because I think it's good practice for you watching to do it yourself. So there are some resonance structures here. If you don't feel comfortable with resonance, please feel free to do it. But I'm just showing you now a general scheme, right? But this will be very important. And then our nucleophile that just left has now a negative charge, right? So now that it has a negative charge, there's also a positive charge, and it looks a lot similar to this, right? So we can just attack it. So let's attack it. It attacks, and then we get something like this, right? Sort of similar to this. It's the exact same. We're getting the same compound where the double bond is now not a double bond anymore, right? But in this case, this reaction is very favorable, right? And favorable reactions happen very quick. But in this case, it's not favorable. In fact, I don't think this can even happen at all if you were to do it in a lab setting. And why is that? Well, I want you to take a close look at our starting molecule and then our ending molecule, right? So our starting molecule was this benzene right here, and then our ending molecule was this. The big difference is this molecule is aromatic, right? Does it satisfy every rule that we have? We have sp2, 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 sp2. They're all in the same plane. We have 1, 2, 3, 4, 5, 6. If we do 4n plus 2 equals 6, n is equal to 1, right? So it satisfies that. Are they conjugated? Yes, there's one carbon after it. So this molecule is aromatic, but what about this molecule? Well, it doesn't satisfy the 4n plus 2 because we only have 4 pi electrons, right? This molecule is sp3 as well as this one, so it's not in the same plane, so this is not aromatic. So we went from an aromatic molecule to a non-aromatic molecule, and that's what makes this so unfavorable. I told you before that molecules want to be aromatic because it's evenly charged, their charge is evenly distributed, everything is fine. But now, if we react it with an electrophile and nucleophile, we have something that's not aromatic from something that was aromatic. So in that case, this reaction is really not favorable. And I drew a reaction coordinate here, right, where we have the reactant on this side. This is energy, so the higher you are, the higher energy. So our reactant is in lower energy than the product. And if you remember stuff from chemistry 6b, if you don't, it's okay. But this is a graph of an endothermic reaction, right? So the products are in more energy than the reactants, which means their enthalpy will be positive, which means it's endothermic. It needs heat or energy to be put inside for it to go through. So that's why it's not going to happen. Remember, we went from an aromatic to something that's not aromatic. So because of that, this reaction doesn't happen with a nucleophile. But there is something we can do here to make it aromatic again, right? If you remember, go back to 40A, we saw two reactions that made double bonds, right? And those reactions were elimination reactions, where E1 and E2, right? So in this case, we can use that to our advantage when we're doing something like this. We can do an E2 reaction. So what if instead we react it with a base? So let's try that reaction out. So our nucleophile is our benzene ring is gonna attack that electrophile. Then it's the base is going to leave. Okay, and then I'm gonna put the electrophile on the top here. I'm gonna put the carbocation right here. And then there is also a hydrogen here, right? And then we also have that base, right? So now, instead of the base attacking that, we can form a double bond where it attacks that acidic hydrogen, and that bond goes here to form that double bond. Like that. We still have our electrophile here, but now we have HB. So you see the difference in our starting product is aromatic, right? Our starting product here is also aromatic. We added that electrophile here, And then look at what happened here. We also added that electrophile, right? But now our product here was not aromatic, but now because we added a base and we did an E2 reaction or an E1 reaction, now it's aromatic. So this is the main basis and summary of what you're going to do today. You're going to try to make products off of benzene that have some derivative, some like chain here, and you want to figure out how to preserve this aromaticity because it's really, really important. And the way we do that is we do it with an E1 or an E2 reaction. In most cases, it's going to be an E2 reaction because E1 you need certain conditions. So this is an E2 type of reaction, right? This is not an E2, this is an E2 type. So it's similar, but it's not the same as an E2, okay? So let's try an example of this. I know you're looking at this, you're seeing, oh my goodness, this is so hard, but let's think it through slowly, okay? So let's see what happens. So at first, when I'm looking at this, I see that there's two double bonds here. Well, there's three double bonds here and one double bond here, but this molecule has one double bond that we can attack and this one also has a double bond that we can attack. So the main emphasis here is which double bond is going to attack, right? So let's think. If I attack the double bond right here, this is going to be electrophilic, right? And we don't want that because we wanted the benzene to act as a nucleophile here, right? As you can see here. So if we do that, that's not going to happen. But if we do this, this double bond attacks that hydrogen, then this will be a positive charge right here, right? A carbocation. So let's try to do that. That F bond is going to go to that F. And then we do it this way, right? So if the carbocation went here, it's a primary carbocation, which is bad. So we would want the carbocation to be right here, which is a secondary, which is a lot better, right? So we have this is the hydrogen, and we have this positive charge here. And then we have the fluorine that just left. Oops. Right? So now we have something that's very electrophilic, right? This is very, very electrophilic. And now we also have something that is a pretty good nucleophile, right? If I say so. So then we can attack it. We can attack this over here. So now we're gonna get something like it doesn't matter where it goes. I'm gonna put it at the top. So you see how there's 1, 2, 3, 3 carbons. So we have 1, 2, 3, right? If I react it here, there's one going opposite sides. So we have this, sort of like a V, okay? And we also have this fluorine atom right here, right? So what's missing? We have this carbocation right here, but we also have a hydrogen here. And remember what I said? This molecule here, this starting material was aromatic, but now this isn't aromatic. This is not aromatic. So to make it aromatic, we need to do an E2 type reaction. And look at what we have. We do have that acidic hydrogen that we can take and that double bond can form, which means it's going to look something like this. That plus H. Oh, okay, that's a lot to take in. So take a look at this reaction closely, and then I want you to notice that in this case, if we took the hydrogen here and reacted it there, um, if we took the double bond from the benzene ring and reacted it with the hydrogen with this acid, this isn't strong enough to react to the electrophile the carbocation that we formed. Because this has a lot of double bonds here, it's donating to that electron strength, which makes this a better nucleophile, right? So if this attacks the acid, it gains that carbocation on the second. And now this is it's a good nucleophile, better than this one. So then it can attack that carbocation, forming this type of molecule. And then we have an E2 type reaction here to complete and stick with our aromaticity, and it preserves it, right? We went from this aromatic compound to this aromatic compound, but we just added this type of alkyl chain here, right? So this is a little complicated, so take your time with this. And I hope that I explained it okay. So this is just an example. So I'm going to show you now a list of reactions and reactants that you need to know. Some of these you don't need to know the mechanism. So this is a mechanism, right? We're showing how electrons are flowing from one atom, one molecule to the next. But in some of these reactions and reactants to know, there's like, it's a lot of organic chemistry that we don't know how to do yet. And I'm going to show you a few a few of mechanisms that may be a little too complicated. And I struggled with it a lot too. I kept asking why, but it's very advanced organic chemistry, and it's okay if you don't understand it, but try to poke your head around it a little bit and try to understand it, okay? So the first reaction we had to know is called nitration, and nitration is going to add a nitrogen, a nitrate group, right? And then we have a benzene ring, and this is nitric acid, HNO3, under H2SO4, which is sulfuric acid, which is going to be our solvent here. And through a series of reactions and mechanisms here, you have this NO2 at the top of the benzene ring, right? And then we still preserve this aromaticity. So this is called nitration. Benzene plus HNO3 under acidic conditions yields a benzene with a nitrous, with this NO2 group at the top, okay? Because we have this NO2 group now, we have something called, or I think it's called ammination. I'm not really sure what it's called, but I just think of it as ammination because we make an amine here, right? So if we have this NO2 and we react it with H2, right? You remember hydrogen gas plus a catalyst. This is any catalyst. We get this ammonia ion NH2, this amine group right here, right? Again, if I'm showing you these without the, later on I'll have something where we learn the mechanism, but these are you just have to know them. It's memorizing, right? But try to learn it. So yeah, ammination. The third one is called halogenation, right? You've heard this before in 40A, where we add a halogen to a in the 40A it was an alkane, so it was radical halogenation, right? But this time we're going to do it with a benzene ring. So we're going to react this benzene ring with any halogen. Usually it's Br or Cl, so we reacted with dibromine or dichlorine, right? Under this is, oh, sorry. This is called our Lewis metal. So we have a iron, Fe, iron, and then a tribromine, and then trichlorine. Yes, this is weird. I also agree that I think it's really weird, but it is something that you have to know, and I'm sorry. But what it does is it adds it on the top of the benzene, so it still preserves the aromaticity. I'm so sorry, dude. This looks really bad, but it's okay. We have the bromine or the chlorine on top, depending on what you added, and then that is halogenation of benzene. The next one is coined after chemists, so it's the Friedel-Crafts Alkylation. So we start with our benzene ring again, right? And then we have this R group, and the R group can be whatever. It can be any methyl chain, it can be anything. And then we have it connected to a halogen, right? So think of it like this, sort of, right? Where you have something like that. And then we react it with another Lewis, a Lewis metal, right? Sorry, this is a metal, not a methyl. Metal, right? MX3, it can be any metal. It's usually iron, but we have that. And then now it makes this this compound. Oops, where'd I go? Oh, sorry. It makes this compound where we have the R group sticking out right there. Okay, so that is Friedel-Crafts alkylation. We have that R group right there. This metal is usually either aluminum or iron again. So yeah. And then we have Friedel-Crafts acylation, where it's an acyl now instead of an alkyl, right? Alkyl acyl. So we have this um, this ketone looking group attached to an R group and a halogen, right? And then we have the metal with the trihalogen, and it makes this type of molecule right here. Okay, so let's go into the next one, which is reduction. So the reason why I'm showing you these reactions is that in 40B, you focus a lot on synthesis, right? So if I show you a reaction like, I want to turn this into this, how do you do that? This is why I'm showing you these reactions, because I'm sure that your teacher will test you on whether or not you know how to synthesize this compound from this starting material. And I just want you to get these um, solvents and reactants under your belt so you're ready for that, okay? I know it's a lot and I'm sorry, but you have to do what you have to do, I guess. So then our next one is going to be reduction. So zinc and this is mercury under hydrochloric acid. So we have this Friedel-Crafts acylation, this carbonyl group. And if we react it, we get rid of that carbonyl group and we're left with a methyl group, right? And with whatever R group there is, okay? So I hope that was able to help. Let's go into some mechanisms, right? So again, I told you that these are just some stuff that you have to know, but some of them do have mechanisms that I think should be helpful for you. And I'm just going to play it safe and show you the mechanism, okay? So first up, we have nitration. So in nitration, we have our benzene ring, and then this is HNO3, right? HNO3. This is the compound right here. The N is double bonded to an O, single bonded, and single bonded to an alcohol. It's positively charged, right? If you do a quick formal charge. So, and then we have it under, this is sulfuric acid, H2SO4. So this oxygen here is going to attack the acidic hydrogen while the oxygen leaves. And with that, you get this water compound, right? If this oxygen gets another H, it turns into water, which is now a good leaving group. So this lone pair can come and form this double bond between nitrogen and oxygen. And then this leaves as well. Think of it like an SN2 type of reaction. Because of that, now we have N double bonded to an O and also double bonded to an O. And then this is still positive, so that means we can do substitution where the double bonds get the nitrogen, and then we have this NO2 here. We make the carbocation right here, and then you complete it with an E2 type reaction, and you get this, right? So, oh, by the way, I forgot to say, these are all called electrophilic aromatic substitutions. So the reason why is because you really want something to be electrophilic, right? Something to be something that has a positive charge. Aromatic substitution, where aromatic group substitutes one of its side chains for that electrophile, and it still preserves the aromaticity like always, right? So that is nitration. Again, just a quick rundown. Oxygen from the OH attacks the H from the sulfuric acid, and then it becomes water, which is a good leaving group. It leaves while the lone pairs from oxygen make a double bond between N and O. Then that makes this nitrogen still positively charged, which means we have a good electrophile and this is a mediocre nucleophile, so we can attack it here. And then because of that, we form a carbocation, right? And then we still have a hydrogen from up here. Sorry, not from here. This is from up here. Let me change that real quick. Hydrogen from right here. And then we can grab that, and then this can form that double bond there, right? Grab that from the double bond there. This is the oxygen from the sulfuric acid. It doesn't matter which one, but we make this NO2, okay? Next up, we have halogenation. So again, it's the dibromine plus the FeBr3. So this is the compound for FeBr3, right? So this bromine will attack this iron Br3 compound. Again, this is very advanced organic chemistry. I was just taught this, and I'm going to tell you what I think is supposed to happen and what I learned. So when it attacks that, it gets a formal charge of a positive, and this iron gets a formal charge of a negative. And then this makes a good leaving group, and this is also slightly positive. So then we can attack the bromine with the aromatic compound, the double bond. We just have the Br, right? And then again, we have this positively charged, and to make it aromatic again, it's going to, that Br will take the H that's here and form this double bond that we get right here, okay? So again, Br attacks the Fe, the the aromatic ring attacks the Br, while the Br to Br bond leaves. And then you have the Br on the aromatic ring. And then you can do an E2 type reaction. I didn't show it here, where you form that double bond again. Okay, next up we have Friedel-Crafts Alkylation. And for this, I'm actually going to show you in real time how it's done, because I want you to get something, to get this very important concept, right? So we have this aromatic ring, right? And then this Br will be reacting with, right, the same FeBr3 compound that we saw earlier. It goes like that, right? Oops, do I have room for this? Br, Fe, Br, Br, and then Br here. This Br now has a positive. This Fe has a negative. I'm just going to move this down over here so we have more room. So now, once it gets that positive, we can let it leave, right? And then what happens when it leaves? We form a carbocation right here, right? 1, 2, 3, 4. Yeah, on the fourth carbon. And then we have Br, Fe, Br, 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 like that, right? And then we also have this aromatic ring, okay? But look at what's going on here. We have a positive carbocation, right? But we also have a secondary carbocation right here, which is more stable. So what it can do is it can hydride shift. It can take one of the hydrogens and it can shift over here, making it a secondary carbocation instead of a primary carbocation, right? And you've seen this before. It was in, I think it was in Chem 40A where you have that hydride shift. Again, whenever you're making carbocations, please look everywhere, up, down, left, right, to look for hydrogens that can make it a better um, carbocation. So now we have a secondary carbocation, which is good. We have a carbocation, and we also have our benzene here, which can attack, and it will attack that carbon, right? So we get something like this. I'm going to put it on the bottom. So we have, I think, 1, 2, 1, 2, and then, yeah, I think that looks right. So we have, if we attack it here, we have 1 carbon going off the sides, which is true, and then 2 carbons off the other side. Yep, that's perfect. Which the carbocation is right there. And we also have a hydrogen here. Br, Fe, Br, Br, and then Br. And then now it's very complex, but what's going to happen is, so what's going to happen is that the bromine will take the hydrogen while this leaves. So it's a really weird mechanism, but it's okay if you don't know it. I don't really, they didn't really teach us this, but it's a very advanced organic chemistry type of reaction, but it's okay. It's okay if you don't know it. And then we form this double bond, but we still have this alkyl group right here, right? So we turned, so a common mistake is that if you reacted it with this carbocation, you're gonna form something like that, right? Where we have 1, 2, 3, 4. Oops, sorry, I missed one. Where you have 1, 2, 3, 4, because you reacted it with this. But you have to understand that this is a primary carbocation, which is really bad. So we want to put it at the secondary term, which gives us our correct compound of this. Okay. Again, this is very complex, so take your time with this. I'm here to explain anything. You can come to my office hours if you'd like. But yes, I'm here, and then you're going to be okay, I promise. Okay. And then now our last one is Friedel-Crafts Acylation, which is the exact same thing as the one that we saw before with this reaction, right? It's the same mechanism. So let's say we have something like this, and then we react it with the Cl and then this double bond here, right? And then now we have Al, oh, let's do Fe, FeCl3, right? FeCl3. So what's going to happen is that FeCl, what's going to happen is that this chlorine will attack the iron, which makes a weird compound ClFeCl. This chlorine is positively charged. This iron is negatively charged, which means it's a good leaving group. So we can make it leave. And then we have something like this, where this is a positively charged carbocation, right? But it's pretty stable because it has a double bond here, and this oxygen is giving it some electron density. And then we still have our aromatic ring, which can react with that positively charged carbon, form something like this. I'm going to put it on the bottom again. So if I do that, I get something like this, right? Where I have 1 carbon here and another carbon here. So I have in total 2 carbons. And then I still have my hydrogen here and then a positive charge here. And then we also have the FeCl3 that just left, right? And then this is negatively charged, still positive. Can attack this, make that double bond while this leaves. And then we get our Friedel-Crafts Acylation compound, a ketone with an aromatic ring attached to it, right? And then we have, these don't really matter, but yeah. So I hope that clears everything up. I'm sorry, this is a very, very loaded chapter. But please feel free to reach out to me if you have any questions, and I will see you on the next video. Good luck studying. Have a good one.